All right, if you missed class on Tuesday, then you're going to need some of these notes. So we're filling in that we've got the volume is a fixed amount of gas held constant, temperature varies inversely, and then we rewrote Boyle's law. You have an opportunity for a sample problem there if you need to work that. Charles' law, the volume of a given amount of gas, it means we're not adding any more gas, is directly proportional to the Kelvin temperature at constant pressure. So that looks like this, V1 over T1, V2 over T2. We always have to have Kelvin temperature because this means that the temperature will never be zero or never be negative. We get to Kelvin by adding 273 to the Celsius temperature. If we have Celsius, if we have Kelvin and we need to get back to Celsius, we subtract 273. This is important because dividing by zero would be undefined, or multiplying by zero would mean that we had a zero volume or a negative volume, which we can't have. Here's another sample problem that you can work with Charles' law. Gay-Lussac's law says that the pressure of a fixed amount of gas varies directly with the Kelvin temperature when the volume remains constant. That just means that the container is fixed. It can't get bigger or smaller. So this is P1 over T1, P2 over T2. You can rewrite that P1 T2, right? So we cross multiply P2 T1. Here's a sample problem that you can solve. So the combined gas law takes all three of these ideas, Boyle's law, Charles' law, Gay-Lussac's law, and puts them into one equation together. P1V1 divided by T1, P2V2 divided by T2. Another way to write this would be P and V1 times T2, PV2 times T1, all right? So we solved this problem together in class. You can pause the video if you need to fill in. Remember, we're filling in our chart, changing this temperature to Kelvin. There's the answer. Remember, we get this. We're going to multiply, 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 and then divide by 303, divide by 404, because those two things are connected to the unknown. Here's another example problem that you can work through if you need to do that. That's not a sign. That's just for more practice. Bethany, do you mind closing the door for me? We went over these section assessment questions, so I'm just going to briefly talk through here. I see that you can stop the video and take some notes. If we're stating the relationship among the three things, pressure, temperature, and volume, that we're going to be using the combined gas law, and there it is, so we would write that out. Number 15 of this section says, if we have equal amounts of gas, what's directly proportional, and we see that volume and temperature and pressure and temperature are directly proportional, and pressure and volume are inversely proportional. When one goes up, the other goes down. The answer to this question is we have to look at what we know and what we need to know. So we have a volume, a temperature, and a pressure. And if we're asked for a predict a volume, that means a new volume, that's what we would be looking for. Well, we can't have a lot of unknowns. So we would have to have a new temperature and a new pressure at this new altitude. This would be using the combined gas law to solve that question. Number 17 says, infer why gases such as oxygen used at hospitals are compressed. That would be so that we can get more oxygen in the same tank. And then, why must compressed gases be shielded from high temperatures? Because they would expand too quickly and explode. And then, why must compressed oxygen, what must happen to compressed oxygen before we can breathe it? And it must be compressed because our lungs can only take in oxygen and air that is at a pressure that we're used to dealing with. We solved this problem together in class. So a rigid container, this idea of a rigid container lets me know that there's no V2. And we can read the question knowing that. We have a pressure of 660 torr, a temperature of 22 degrees Celsius. We add 273 to that. There's our new Kelvin temperature. And then the increased temperature was 44.6. So 317.6 is the new temperature. Go ahead and round that to 318 because we didn't have a decimal number here. So we cross multiply here, so 660 times 318 divided by 295, because that's connected to the unknown. So our calculator shows 711 torr. We're going to round that for 2 sig figs to 710 torr. Turning the page and going on, we got some notes on what it means to talk about the ideal gas law. So now we're going to start to consider number of particles. When we add particles of a gas to a container, that also increases the pressure. Now, Avogadro, we know him from Avogadro's number, and the number 6.02 times 10 to the 23rd. That's how many particles are in 1 mole. And we are going to see here that equal volumes of gases at the same temperature and pressure contain equal numbers of particles. So there's some examples of that in the book that you can look at. So from this, we get an idea of molar volume. And the definition of molar volume says that 1 mole of a gas occupies, the volume that 1 mole of a gas occupies at 0 degrees Celsius and 1 atmosphere of pressure. That's the definition. And that amount is actually 22.4 liters. We have to know the value for STP, which is 0 degrees Celsius, 1 atmosphere of pressure. Also know pressure can be in different volumes, kPa, torr, and millimeters of mercury. So Avogadro showed experimentally that 1 mole of any gas at STP has this volume. This means that we can actually use 1 mole over 22.4 liters as a conversion factor, or 22.4 liters over 1 mole, whichever one we need to answer our question, but this only works at STP. This doesn't work if our pressure and temperature are not STP. So let's look at how we solve a couple of problems here. So if we have, so you can read the question there on your page, we have 2 kilograms of methane, but we are not allowed to use kilograms to find molar mass. Pardon me. So we've got to convert that to grams. So 1,000 grams is 1 kilogram. And then we go to molar mass because this is happening at STP and we're looking for a volume. So now we say 1 mole over the molar mass of methane. And then we say 1 mole takes up this much volume because that's what Avogadro's principle tells us. So 2 times 1,000 divided by 16.043 times 22.4 gets us 2,792 liters. We're going to adjust that for 3 sig figs, so 2,790 liters. Here's another way. I'm going to skip this example. This one is worked out in the book, so you can follow along with that one. Let's look here. When we're given number of moles at STP, then it tells us it's nitrogen, but we don't really care about that because we're not asked for grams. We're just asked for volume. So if we have 0.045 moles, we know that 1 mole has this volume. So we're just going to multiply that and get 1.03 liters. Another one, we have a 1 liter balloon, and it says, what's the mass? So this time, we know we do care what the gas is because we need molar mass. 1 liter of CO2. So 1 mole has this volume, so liter cancels. Now I have moles of CO2, but I want grams of CO2. So now I'm going to say 1 mole of CO2 has this mass, 12 plus 32, gets us to 44. So 1 divided by 22.4 times 44.0 gets us about 2.0 for the rounding there. Okay. This next one, the only caveat we have here is that it asks us for milliliters. So here we go from grams to moles using the molar mass. Then we go from moles to liters using this the Avogadro's molar volume idea. And then we're going to multiply by 1,000 because milliliters, there are 1,000 milliliters in 1 liter. So our answer is 103 milliliters. 102, depending on what number you use here. Number 23 and 24 were assigned for homework, so you'll need to upload your work for that. Let's get a couple of more questions, a little bit more questions here, and I'm going to see if I can finish this before YouTube won't let me upload this. So here we're going to say this is the ideal gases. Gases, they follow the assumptions of the kinetic molecular theory. The ideal gas law is PV equals nRT. PV equals nRT. That is the law that we are using all the way down through here. Pressure can have any of these three units: atmosphere, millimeters of mercury, or kilopascals. Volume always has to be in liters. N is the number of moles. R is the gas law constant, which is going to hold all of the other four units. And then temperature has to be in Kelvin. For the gas law constant, we can have three values for this. The value we choose to use would be dependent upon the pressure unit in the question. So if the pressure is in atmospheres, we would use 0.0821 liter atmosphere mole Kelvin. If it's in kilopascals, we would use 8.314 liter atmosphere mole Kelvin. These are just the words, right? They're going to cancel everywhere. 62.4 liter millimeters of mercury mole Kelvin, right? So let's solve a problem. Calculate the number of moles. So here I know that N is my question, contained in a 3 liter, right? There's the volume, vessel at 300, that's the Kelvin, that's the temperature, pressure 1.5 atm, since the pressure is in atm. The unit I'm going to use for R is 0.0821, and then I'm going to fill in 1.50 times 3 equals, there's my N, my unknown, and there's my gas law constant, and then the temperature. So here is the unknown, right? N is our unknown. So we're going to multiply and then divide by these two. Divide by this, divide by this. We would rewrite that if we needed to. The answer is 0.18 moles of N. Let's look at one more here. All right, so again, we're solving. I'm going to go down to 26 because it has a different pressure unit. 143 kPa's is what it says the pressure is. The volume is 1 liter. It says we have 2.49 moles of the gas. And the question is, what's the Celsius temperature? So here, since the pressure is in kPa, I'm going to use the R that matches kPa, so that's 8.314. And then I plug in 143 times 1 equals 2.49. Again, our law is PV equals nRT, right? So we're just plugging in. There's the R, and then we're solving for T. So to get T by itself, we would divide, right? 2.49 and 8.314. So this times this, divided by this, equals 6.91 Kelvin. But it said Celsius temperature. So now we're going to subtract 273 and get negative 266 degrees Celsius. Here are the answers for the next couple. You can check yourself on that. You'll show the work. So 27, 28, and 29 were also assigned. You have 5 questions for homework. So you had some answers there, but the answers are no good without the supporting work. I hope that helps you fill in the gaps for what you missed in class today. We'll talk about how you can get your quiz. You will not have to take that on Thursday. I'll send you some more information on that. Have a great day.